Hello and welcome to Lesson 42 of Additional Maths with Mr. Barrow. Today we're going to be looking at what definite integrals actually find. They find area under a curve, okay? Or area between the curve and the x-axis. I'm going to show you how to use definite integrals to find that area, and I'm also going to try to explain why it gives you the area, why integrating gives you the area between a curve and the x-axis. Okay, so before we look at this worked example, find the area of this shaded region. Okay, so the region here, the green shaded area between x is -3 and x is 1 under the curve of y equals 9 minus x squared and above the x-axis. So to find that area, we need to know what to do. The process of finding areas is definite integration. So last lesson, we looked at how to do the process of definite integration, and we did not understand what it was. We just followed a process and found an answer to a definite integral. So the process was, if you were asked to integrate between two limits a and b, you integrated first. So f dashed x became f of x. And then you substituted in the two limits and subtracted. So you substituted in the top limit first, and so f of b, and then you subtracted the result when you substituted in a. So subtract f of a. And that actually gives you this area here, okay? The integral between a and b of f dashed x with respect to x is actually the area under the curve of y equals f dashed x. So between x is a and x is b. Now what I'm going to do is I'm going to try and explain why that gives you the area, why integrating between those two values gives you the area. So here we have. Why do definite integrals find the area below a curve? So imagine we have this curve, y equals f of x. Let's say that the area up to the x value x, let's give it the value a of x, where a is some function which gives us the area up to the x value x. So a of x is the area from the x is 0 up to x is x. Now, imagine I wanted to get the area between two x values. So between an x value of x and an x value of x plus h. Well, I've defined the area up to an x value as a of that x value. So the area up to x is a of x. The area up to x plus h, so all of the area, so I'll use a different color here. So all of this sort of magenta color area, so all of that area would be a of x plus h. And if I wanted just the area between x and x plus h, I would subtract one from the other. So the area of this section here, the yellow section, is area of x plus h, subtract the area of up to x. Okay? So, how do we find that? Well, let's have a look at trying to define boundaries for this area. So lower limits and upper limits for this area between x value of x and x value of x plus h. So that area, I've redrawn that area It has a width of h, and it looks like that. If I want a lower limit for that area is definitely bigger than the rectangle where I take the lower y value as the top of the rectangle. So I've done that on the left. So I've taken the lower y value as the top of the rectangle, and that area is h across, and it's a rectangle which has, if we take the lower y value, that lower y value is f of x. As you can see, f of x is the y value when we substitute x in. Okay, so f of x is that y value. So the area of that rectangle is h times f of x. Okay, so our area that we want is definitely bigger than that. And it's also smaller than the area if we take a rectangle with the top y value. So that's what we've got here. The top y value, I've gone across from the top y value and I've created a rectangle from that y value. So the area we want is below that. Okay. I've put less than or equal to for both of these inequalities because if the curve was actually horizontal at between those two values, then it would be equal to both of them. Okay. So it's less than or equal to the greater rectangle. And the greater rectangle has a height of, well, the x coordinate is x plus h. So the y coordinate here would be f of x plus h. So it would have an area of h times f of x plus h. So I know that the area that I want, and we've already stated what that is a of x plus h minus a of x. I know that that is between h times f of x and h times f of x plus h. I know that, okay? So what can I do? Well, I could divide everything, all parts of this inequality by h. I'm allowed to do that and the inequalities don't change because h is some positive value. So if I'm dividing by a positive value, the inequalities won't change directions or anything like that. So I'm going to divide by h, and this is what I get. So all three parts of this inequality will be divided by h, and then this will be true. That the value of a of x plus h minus a of x divided by h is between f of x and f of x plus h. Okay. The next thing I'm going to do is I'm going to take the limit of all three of these parts of this inequality as we make h tend towards 0. So as we bring the two vertical lines closer and closer together, so as we bring x and x plus h closer and closer together, so h tends towards 0, so x plus h gets closer and closer to x, what's going to happen to these values? Well, if I bring x plus h closer and closer to x, f of x isn't going to change. It's still going to be there, okay? So the left side of my inequality will still be f of x. The middle part of my inequality, I'm going to write, let's find the limit as h tends to 0 of this expression a of x plus h minus a of x over h. And you might recognize that from the start of differentiation, and we'll come back to that in a second. And then if I find the limit as h tends to 0 of f of x plus h, well, as we make h tend to 0, okay, so as we're bringing x plus h closer and closer to x, then f of x plus h will get closer and closer to f of x. So as h tends to 0, f of x plus h will also tend towards f of x, which makes sense because if I make h 0, then I've got just f of x. So that's quite interesting. So now I've got that this middle expression here is greater than or equal to f of x and is less than or equal to f of x. So I know that that means that it equals f of x. Because if it's no greater than it and it's no less than it, then it has to equal it. Okay? So coming back to what this middle expression means. The limit as h tends to 0 of a of x plus h minus a of x over h. You might remember back from differentiation from first principles that the definition of the derivative of a function, okay, so f dashed x or dy by dx was equal to the limit as h tended to 0 of f of x plus h minus f of x over h. So that's what the derivative of f of x was. So this middle expression, we're replacing f with a. So the a is the function. So this is really a dashed x, the derivative of the area function. So we have a dashed of x has to equal f of x. So the derivative of the area function is f of x. And therefore, the area function, to get the area function, we need to integrate f of x with respect to x. So that's why you get area if you integrate the function you have that you need to find the area below. Okay? So that's the proof. It's not extremely important that you fully understand that proof. It's nice if you do. Okay? It'll come to you over time, and the more you practice integration, the more you'll get a sense of what it means. Okay, so if you didn't completely follow through, that's okay. You're a novice learner, and I didn't understand integration at all for many years, despite being able to use it. Okay, so it'll come with time as you master this process. So if I wanted, therefore, this area here between 5 and 7, then really what this is the area up to 7 subtract the area up to 5. Okay? And the area function is the integral of f of x. So really what I want to do is I want to integrate f of x, and that will give me the area function. And then I want to substitute 7 in, and then I want to substitute 5 in. So that's why we substitute the upper limit, and then we subtract the substitution of the lower limit. Okay? So let's put that into practice and actually do an area under a curve. So find the area of this shaded region here. The area below y equals 9 minus x squared from x is minus 3 up to x is 1 and above the x-axis. So our process, we understand that we need a definite integral to find this area. And the definite integral that will find this area is the following one. It's the integral from the lower limit minus 3 up to the upper limit 1 of 9 minus x squared with respect to x. So if we integrate that and then we substitute the numbers 1 and minus 3 and subtract, we will get the area required. So first step, integrate and put it into square brackets. 9 integrates to 9x. Minus x squared integrates to minus a third x cubed. So we increase the power by 1 and divide by the new power. I could put plus c, but remember in the last lesson I explained why we don't need to. Okay, it's redundant. It will cancel out when we do the subtractions. So with a definite integral, you don't put the plus c in. So I'm going to integrate that between minus 3. So I have integrated that, and then I'm going to substitute in the numbers minus 3 and 1. Okay. So the next step is finding this. This is the area function. This is like a of x, and I'm going to find a of 1 and a of minus 3 and subtract the 2. Okay. So we now do 9 lots of 1 minus a third of 1 cubed. So that will give me a of 1. And then we subtract 9 lots of minus 3 minus a third of minus 3 cubed. So always better to do this, especially if calculations aren't too complex, which this isn't, much better to do it in your head because you can easily go wrong by plugging things into your calculator. So get a good sense yourself and then check with your calculator if you want to. 9 times 1 is 9, minus a third of 1 cubed. 1 cubed is 1. So negative a third of 1 is negative a third. So it's 9 take away a third, which is 8 2/3. Okay. Minus, and then the other one, 9 times minus 3 is minus 27. Minus 3 cubed is minus 27. And minus a third of that is positive 9. So it's minus 27, add 9, so it's minus 18. And then 8 2/3 minus 18 is equal to 26 2/3, which is still very ugly because it's a mixed number and we don't like mixed numbers. So 80/3, much better. Okay. Now this is an area, so we have the following to put after it: units squared. We don't know the scale. We don't know if we're talking about centimeters, meters, kilometers, what the units are. So we just say units squared. Whatever the units are for the scale, for the graph, for the context that it's in, it'll be that unit squared. Okay, so that is the area that was shaded before. Okay, so I would like you to have a go now at this one. Find the area of the shaded region for this graph here. The graph's equation is y equals x squared plus 5. And I want you to find the area between x is minus 3 and x is 2 and above the x-axis. So pause, have a go, do the algebra, do as much as you can without a calculator. You could always check afterwards if you've got the fancy calculator, which has the integral symbol with values you need to substitute in. Okay, so this button on the calculator, if you have one of those. Okay, but do the mathematics first before you check with your calculator. Okay, I'll go through the answer now. So the area here is the integral between minus 3 and 2 of the function x squared plus 5 with respect to x. If you integrate that, you get a third x cubed plus 5x, and that's between the limits minus 3 and 2. And when we substitute 2 in, we get a third of 2 cubed plus 5 lots of 2, which is 12 2/3. Minus, if you substitute minus 3 in, you get negative 24. So it's 12 2/3 minus 24, which is 36 2/3. But let's put that as a much more beautiful top-heavy fraction. Okay, 110/3 units squared. If you managed to get that right, really well done. Okay, so a reminder of what we've done today. We have found areas between the curve and the x-axis and between two limits for the x values. We've done that using integration, using something called definite integration, where we integrate and then we substitute the two values and subtract. We also learned the reason why this gives us the area. Okay, the reason why integrating gives us the area between two limits. Okay, why definite integration gives us that area. Remember that it's not absolutely essential that you understand the proof. You won't be asked for the proof, you'll just be asked to use the process, but it's nice to understand where it's coming from. The way I think of areas is I actually think of it as, if I want to find the area between two values, integration actually gives me the sum of infinitely many rectangles that that make up this space. Infinitely many, infinitely thin. So I could split this space up into 2 rectangles, and that would give me a pretty poor estimate for the area. I could split it up into 4 rectangles, and that would give me a better estimate for the area. I could split it up into 10 rectangles, 100 rectangles, 1,000,000 rectangles. If I split it up into infinitely many rectangles, which were infinitely thin, then I get the exact area. So as we tend towards infinity, we get the area. And in fact, as we tend towards infinity, the rectangles become infinitely thin. So what they become is they actually become just the y values. They just become strips, which are absolutely so thin that they just become straight lines. So I think of this as the sum of all those infinitely many thin strips, which are just straight lines, which have y values between the 2 numbers. And then that creates the area between a and b, where a is this value and b is that value of f of x dx. Okay, so that understanding that I'm adding up all the y values between a and b, and that gives us my area, is the best way to understand a definite integral, and will help us with more complex problems that we're going to come to in the following lessons, and why we get certain strange results, which we will get in the next lesson. What you should do now is look at exercise 15.3, so the third exercise in this chapter on integration. So they're all finding areas above the x-axis, below the curve, between 2 values, nothing that's too complex. So go away, make the process fluent, make sure you understand what you're doing in each one, and come back to the next lesson with an open mind as to what this could go to next. Okay, off you go and enjoy.